All right, let's take a look at, first off, the problem from the spring problem. That was a part of the 3 problems I gave you the other day. A vertical spring with a spring constant of 20 newtons per meter is compressed to 50 centimeters and loaded with 75-gram mass and released. Once the mass leaves the spring, how high does the mass fly? There we go. Spring loaded. Okay, we have a spring that's compressed down. It's compressed down by 50 centimeters. So initially, we were up here. And we compressed it down 50 centimeters. Okay, so we have a compression of 50 centimeters. As a mass, the mass is 75 grams. And we have a spring constant K of 200 newtons per meter. 200 newtons per meter. And we're releasing it, and it's a spring load, and it's going to shoot the weight or the mass up into the air. We want to find how high does the mass fly. Well, initially, if the mass was just sitting there, if the mass wasn't there and it was up here, we'd have no energy in the spring. But since we compressed the spring 50 centimeters, we can find the potential energy of the spring, which is the work that had to be done for the spring. Well, how do we calculate the potential energy of the spring? Okay, 1/2 K delta X squared. So we have 1/2 times 200 times 50 centimeters, but we need to put this into meters. So this is 0.5 meters. So we have 0.5 squared. We have to convert this into meters just because if we take a look at our units, we have 200 Newton per meter here, and then we have 0.5 meters that are being squared here. So we need to make sure we get the correct units here. So how much potential energy do we have, Riley? 25 joules, taking 0.5, taking 0.5, squaring it, and multiplying it by 200 and 1/2. At this point right here. It is released and it shoots up in the air. The potential energy goes from 25 joules here to when we go back up to neutral, we have 0 joules. What is the amount of work the spring is doing here? How much work is the spring doing? What is the work of the spring? Dylan? Yeah, 25 joules. Because once again, our net work is your change in potential energy. So the spring is going to be doing 25 joules of work. Force net is equal to mass times acceleration. Force net, oh my bad. Work net is equal to force net times displacement. What is the net force that's being exerted here? Well, I have my net work and I have a distance that is traveling. What is my force net? Honestly, what's our net force? 50 newtons. That is my net force. This object is accelerating. And initially, we have a velocity of 0. I don't know what the velocity is at the point of release. I know the distance that we have traveled, though, is 50 centimeters. Once I get a velocity that at point of release, then it turns into projectile motion. It is an object that will go up and then come back down. Well, what we need to calculate here is what is the acceleration of the object. I'm contemplating here. We have another thing that we have to worry about. Because we have the force of the spring that's pushing it upwards. But we also have force of gravity that's pulling it downwards. So this net force of the spring is 50 newtons going upwards. But we have two different net forces. We have a net force of the spring. We have a force going upwards that's the net force that the spring is exerting without any weight on there. If I just had a spring that's pushed down for 50 centimeters and I let go, it would exert a force, the spring would exert a force of 50 newtons going upwards. But since I have a weight that's on there, it's going to slow the spring down a little bit because I got a force coming downwards also. So I got this force of the spring going upwards, force of the spring going upwards at 50 newtons. But we have the force of the gravity that's pushing downwards. So we have two different forces that's acting on this mass. Okay, this mass, think of it as the mass has two different forces that's exerting on it. I have the force of the spring, which is 50 newtons going upwards. But I have the force of gravity that's pulling it downwards also. So I have two different forces I have to deal with. That's working on this mass here. I have the force of the spring and I have the force of the gravity. Like I said, this is our net force that the spring is exerting. But we have the force of gravity that's slowing it down. Well, what is my force of gravity? Well, I got 75 grams, which is 0.075 kilograms. Times 9.81 meters per second squared. What's our force of gravity, Jordan? Point what? Newtons. So this mass has a spring that's pushing up at 50 newtons, but I have force of gravity that's pulling down at 0.736 newtons. So on the mass, this is the net force on the spring. The mass force net is equal to its mass times acceleration. So we have, to find our net force, we have 50 minus 0.736 is equal to our mass, 0.075 times our acceleration. So we can find the acceleration of the mass. How's it we get for acceleration? 650 what? 656.8. So we have initial velocity is equal to 0. We have an acceleration. We have a displacement of 0.0. 0.5 meters. We can then calculate a final velocity. V final squared equals V initial squared plus 2AD. Well, we have no initial velocity, so we have V final squared is equal to 2 times acceleration times displacement. Take the square root of that, and we can find a final velocity. Hey, we get for final velocity?
25.63 meters per second.
Look at that. Okay, so the object is released. The object is released. Its final velocity is 25.63 when it's released from the platform. Now what this turns into is an object being fired up in the air at 25.63 meters per second. I want to find what is the maximum height. It's going to come up and it's going to come back down. Well, at a maximum height, this V final turns into a V initial upon release. My maximum height up here, once again, our V final is going to equal 0. We have acceleration of negative 9.81 meters per second squared. And we want to find how high will it go. So we want to find a displacement. So we have V final squared equals V initial squared plus 2AD. So we have 0 equals 25.63 squared plus 2 times negative 9.81 times D. Square it, move it over to the other side, subtract by 2 and acceleration. Bennett, what do you get for displacement? 33.48 meters. If you want to add in the 0.05 or 0.5 meters, that would be fine because it's going to go up in the air a little bit. That would be fine also. Add in the 0.5 meters. You good with this? All righty. Take a look at the other problem. The Great Pyramid of Khufu in Egypt has a height of 147 meters, side that slopes an angle of 52 degrees with respect to the ground. Stone blocks with a mass of 1370 kilograms were used to construct the pyramid. It begins to slide down from the top, coefficient of 0.45. Calculate the kinetic energy and the velocity of the block at the bottom of the pyramid. So we have 52 degrees here. It starts sliding down. The mass of this, 1370 kilograms. We have coefficient of friction, 0.45. We have the height is 147 meters. Height is 147 meters. Calculate the kinetic energy and the velocity of the block at the bottom of the pyramid. Now, when we were on the slippery slope of the skis, we had no friction. We neglected all friction. The roller coaster, we neglected all friction. We hope that the wheels and the wheel bearings are greased really well and there's no friction, because if we have friction, friction's going to wear down things, and then errors and failures will start to occur, and then roller coasters fly off the track. That's not good. But this object's going to slide down the hill. Well, what's our potential energy at the very top? What's our potential energy at the very top? Don't know if I use it, but we'll throw it in there. Probably will at some point along the line. MGD, what do we have? What is our potential energy, Katie? you take 1370 times 9.81 times 147. Mass times gravity times our displacement. What's the height of the object? $1,000,000 what? Joules? A lot of potential energy there. Okay? A lot of potential energy. You get hit in the head with that, that's going to hurt. Just a little. Just a little. Well, we can also think of this as an inclined plane. Like I said, there's a bunch of things that we have dealt with in regards to this. You can also think of this as an inclined plane. I'm going to spread this out just a little bit, just to make it a little bit more familiar to us. 52 degrees. We have our mass here. We have gravity. Our force of gravity is equal to our mass times 9.81. Our angle here is 52 degrees. Our coefficient of friction is 0.45. So we can think of this as an inclined plane also. Calculate your force parallel, your force perpendicular. Calculate your force of friction. Which is mu times force normal. Once again, all we're utilizing here is what we've done before. Question, Liam? Huh? Force perpendicular. Your force net would equal force parallel plus our force of friction, which should be negative. Once we find our force net, that's equal to mass times acceleration. We can find an acceleration of the object sliding down. We have an initial velocity of equal to 0. We will calculate our acceleration. We know the height of this is 147 meters. So you'll be able to calculate this distance using your trig. 152, or sine of 52 is 140. Sine of 52 is 147 over d. We can calculate this distance. You can then calculate a final velocity at the bottom and then the kinetic energy. And what we're going to do is we're going to make a comparison to the kinetic energies and the potentials. Okay, I gave you homework for this chapter that won't be due till next week, but you can start working on it. We will have a quiz on Friday. On Friday, I gave you a review sheet here now. If you want to start working on that also. Finish this problem. We'll talk about this at the beginning of class tomorrow. Adios. Have a good day.